Hey everyone, welcome to TitanClass. On this episode of TitanClass, we're going to review a whole bunch of trig functions, inverses, and graphs. Part 1, inverse trigonometry, so we're going to be evaluating inverse trig, inverse composites through the evaluation, and even more fun stuff. Part 2, finding the ABCDs of trig graphs, and maybe a little bit of graphing, but more importantly, finding those key values. And then Part 3, applications. Think Ferris wheels. Those are fun. To ride, not to do trig with. Okay, let's go ahead and get started. Part 1, inverse trig and composites. So I think I got about 30 problems for you, and we'll start with number 1, which I think this section has 10 problems in it. So number 1, we're going to be evaluating inverse trigonometry. So what we have here is inverse tan, and again, we know it's an inverse because it has a -1 exponent, of negative root 3 over 3. So we get into some really difficult stuff right away. So when we have an inverse, we're really looking for what radian measurement gives us this ordered pair or this value. So in normal trig, when we just find our normal evaluation, I'd be asking for what radian in according to the trig function gives me the value, right? Or the ordered pair or whatever. But in inverses, I'm doing the opposite. I'm giving you the trig function, bless you, and I'm getting the value of that trig function or at that value, and I want to find the radian measurement that made this for me. So this one's going to be a little bit more challenging. Now, what we have here is our inverse trig graphs, where we know that quadrant 3 is completely out. Quadrant 1, however, is all 6 positive. So all 6 functions are positive in quadrant 1. In quadrant 2, only 3 functions are negative, and those are cosine, cotangent, and secant. And then in quadrant 4, we've got our other 3 functions that are negative, which is the remaining 3, sine, tangent, and cosecant. Sorry, I forgot that last one. Now, what we do here is we want to find out where tangent is negative. So because we have a negative function here, or negative fraction, because we have a negative fraction here, not friction, fraction, I want to know where that is. So I'm going to be looking in quadrant 4 here. So we really want to find out what the y over x value yields negative root 3 over 3. Well, if we're talking about where root 3 is on the top, I need to be finding an ordered pair that has an x comma y, where the x is the root 3 over 2 and the y is the 1/2. Now, this is going to be the negative 1 over half because I'm going to be in quadrant 4. Now, because the x value leads with the root 3, that gives me my root 3 over 3 value, right? Because if I'm doing y over x or y divided by x, I get negative 1/2 divided by root 3 over 2, which is negative 1/2 times 2 over root 3. The 2's cancel, but you know that I can't leave this in the denominator, so I've rationalized the denominator. And yes, I'm going the long way, just so we can figure this problem out. Negative root 3 over 3 is going to be my answer there. So where is, in quadrant 4, our ordered pair of root 3 over 2 and negative 1/2? And if you're looking at your unit circle or you just have it from memory, it's going to be at 11 pi over 6. Now, 11 pi over 6 is not the answer, and the reason for that is because we can't go around the unit circle to get to that value at 11 pi over 6, right? Because quadrant 3 is completely out of the picture, I can't go through it at all. I can't even like pass by. I'm going to go the negative route, which is faster, or the negative coterminal, if you will. So if 11 pi over 6 is the regular, its coterminal from a negative standpoint is negative pi over 6, which is the answer. So inverse tangent of negative root 3 over 3 is negative pi over 6, and that's our first solution. Okay. Now, the other ones shouldn't be that taxing in terms of time. I will leave that unit circle up though, so we can go ahead and fly through the rest of this section. And again, these are not composites, these are just straight up inverses. Okay. Number 2 is inverse tan of 1. Okay, well, we want to find out where I can get a tangent value of 1. Now that's positive, obviously, so I'm going to be in quadrant 1 here. Well, remember that tan is y over x. And the only way that I can get a 1 value from y over x is if my x and y values are, Titan's barking. I don't know what he wants though. If my y and x values are exactly the same. Well, that only happens at one point, at root 2 over 2 and root 2 over 2, which is 45 degrees or pi over 4. Now, I don't need the negative. My answer is actually just pi over 4. Okay. Moving ahead. Number 3. I'm looking for inverse tan. I don't know why these are all tangent. Hopefully they're not going to continue that way. Inverse tangent of 0. Okay, well, when I talk about inverse tangent of 0, there may be 2 places that this happens, so take a look. When I have a y over x value, I'm looking for the result to be 0, meaning y has to be 0, which means x is going to be 1. So where does 1, 0 happen on the unit circle? Well, it happens here at pi, or 0, and then it happens also at pi. Now, it can't go to pi because we can't have anything that's on the borderline of 2 and 3, because 3 is no good. So the tangent inverse at 0 degrees is going to be 0, right? And again, because I can't have any value on the borderline of 2 and 3, because that's not going to give me anything I wanted. Now, I wouldn't know that anyway, because this is a positive kind of value. I know 0 is not positive or negative, but I'm not going to go all the way around for 0 when 0 is here, right? Because that doesn't make any sense, because that would be in negative territory anyway, and tangent isn't even over there, right? So, moving on. Number 4. Okay, where's number 4? Inverse sine of negative root 3 over 2. Okay, so again, the first thing we want to look at is this a negative or a positive value? Well, clearly it's negative because we have the negative in front of the root 3 over 2. So where is sine negative? Well, sine inverse is negative in quadrant 4. So we want to find out where we can find a negative root 3 over 2 value for sine. Now, that actually is going to occur down at 5 pi over 3. Now, 5 pi over 3 gives me that value of sine, or my y value is negative root 3 over 2 here at 5 pi over 3. But again, the answer is not 5 pi over 3 because I'm in quadrant 4 with a negative value. I'm going to have to go the other way because I can't go around. So I'm going to have to go the short way, or the negative side. So the coterminal of 5 pi over 3 on the negative side is going to be negative pi over 3, which is my answer. So number 4 is going to be negative pi over 3. Okay? Flying along right here. Hopefully. Okay, number 5. Inverse cosine, this is an easy one. Inverse cosine of 1/2. Okay, well, again, I'm looking for the x value at 1/2. It's a positive value, so I know that I'm in positive territory. I know I'm in quadrant 1. And where my x value is 1/2 only happens at one place on the unit circle in quadrant 1, and that's going to be at pi over 3 radians. Okay. So again, your knowledge of the unit circle is going to be super, super important here. Otherwise, you're going to struggle on things that really should be something that's rote memory. Number 6, inverse tangent of root 3. Okay. Now, kind of like, not like the other problem that we did with the tangent value on number 1. When tangent is root 3, that means I'm looking for an xy coordinate where x is 1/2 and y is root 3 over 2. Because when I divide them, the 2's will cancel out, right? So I would have root 3 over 1, which is just root 3. This is a positive value, and tangent, obviously, like all other functions, are positive in quadrant 1. So I'm looking for my value on the unit circle where my tangent value is going to be this particular ordered pair. And again, just like the last problem we did actually, this only happens at pi over 3. So on, or in quadrant 1, my value or radian measurement is pi over 3. He's barking a lot. Okay, because that's my ordered pair. Maybe he's hungry. I don't know. Number 7. Okay, inverse sine of 1/2. Okay, so I'm looking for where the y value is 1/2 on the unit circle. Tighten here. Well, again, this is a positive fraction or a positive ratio, so I'm going to be in quadrant 1. I want to know where the y value is 1/2. So my y value is going to be 1/2. He's barking so much, oh my gosh. At pi over 6 radians. So number 7 is pi over 6 radians. Okay, number 8. Inverse tangent of the square root of 3. I feel like we did this one already. Yeah, we did, because this one's negative. I'm like, wait a minute, we did this one already. Okay, so this one's just the opposite of number 6, actually. Which it's literally the opposite of number 6. Okay, so I'm looking for where the tangent value is a negative root 3, meaning my y divided by x value is negative root 3. Well, tangent is negative in quadrant 4. So where can I receive a value that has my 1/2 and my root 3 over 2? And that's going to happen at 5 pi over 3, but it has to be a negative version. So this particular one is going to be my negative pi over 3 value, right? Because it can't be 5 pi over 3, because otherwise I would have to go through quadrant 3. I can't. Because I need a negative here, I'm going to cut down on the negative side and go to 5 pi over 3, which is negative pi over 3 as in distance, right? Number 8 is done. Number 9. Inverse cosine of 0. Wow. Okay, so where am I going to find a cosine value of 0 or an x value of 0? Well, they only happen in 2 places, right, on the unit circle. Here at pi over 2 and here at 3 pi over 2. Now, I can't have a cosine value down here, number 1, because we didn't really specify for a negative. And that takes this out anyway, because cosine, it doesn't exist down below on quadrant 4. So it has to be this value up here at pi over 2, which is the answer. So what radian measurement gives me an x value of 0? And that's going to be pi over 2. Okay? Number 10, and this is the last one in this section. Number 10 is inverse cosine of negative 1. Okay? So where is my x value, negative 1, on the unit circle? Well, now this one I actually can get a value for, because where is cosine negative? Well, cosine is negative in quadrant 2. And negative 1 is here at pi radians. Now, how we said before I couldn't have a value here on the axes, well, this is specific because it's not 0. This is an actual number that has a negative operator in the front, which is telling me to go to the borderline. When it does that, because it's not 0, I can go there. So my actual radian measurement when x is negative 1 or when inverse cosine is negative 1 is going to be pi. And that is a value that does work, and that is my answer. Okay? Let's go ahead and get to the next set, which is going to be composites. Okay, number 11. Inverse cosine of cosecant pi over 2. Okay, so what I'm looking for when I have a composite is we have to go from the inside out. So first, I want to evaluate cosecant of pi over 2. Straight up, no craziness. Just tell me what cosecant of pi over 2 is, and then substitute that value into the same parentheses and find inverse cosine at that value as well. Now, what is cosecant of pi over 2? Well, let's remember the unit circle and what cosecant is. Cosecant is 1 over sine. Well, what is the sine value at pi over 2? Well, pi over 2 is up here. Well, the sine value is 1 up here, right? So what is 1 over 1? Well, that's just 1. So what I'm going to do here is I'm replacing cosecant of pi over 2 with inverse cosine of 1. Well, now we ask ourselves the question, where is cosine inverse 1, or where is x 1? Well, that only happens at one place, and that's going to be at 0. So my answer to this entire thing, this inverse, is 0. Okay, I'll go ahead and erase these. And I think there's 10 in this section. So number 11 is 0. Okay, and again, we're just working from the inside out on these functions. Find the exact value of that measurement and then substitute it into the inverse. Okay, so number 12. I don't know why I'm going higher up. It's weird. Inverse sine of cotangent 3 pi over 4. Okay. Well, again, I'm going inside out. So what is the cotangent value, or the x over y value, at 3 pi over 4? Cotangent of 3 pi over 4 is, well, the value, the ordered pair, is Negative root 2 over 2, root 2 over 2. So x over y of 3 pi over 4 is negative 1. So I'm going to replace that cotangent of 3 pi over 4 with a negative 1. Now I have to ask myself the question, where is sine negative 1? Okay, now, this is, again, one of those instances where I'm not asking for a 0 value. I'm actually asking for a real value. Where is the y value negative 1? Well, it's going to be right here at 3 pi over 2. But because it's not 0 and it's asking for a value, I can evaluate this number, or I can evaluate this trig function. Remember that I'm not allowed to go around to or through quadrant 3. I'm just going to go down the other way. So inverse sine, or my y value, is negative 1 at negative pi over 2. Final answer for that one. Number 13. Okay, sine of inverse cosine 11 over 13. Okay, now this one has a different setup and a different makeup. It's still the same process somewhat, but when we have the inverse on the inside and the sine value or the trig value on the outside, it's almost all the time going to be that I have to draw a right triangle. And here's what the proof is. 11 over 13 is not on the unit circle in any way, shape, or form. So that is an indicator where we're going to have to draw a right triangle, use Pythagorean theorem, and solve for the missing values. So where is cosine 11 over 13, or where's the inverse? Well, I'm going to have to draw a right triangle for that on the unit circle. 11 over 13 is a positive value, and cosine is positive in quadrant 1. Look at that triangle. That is so nice. Take a look at that. Well, maybe that box wasn't so great. Anyway, we know the cosine is ka, or adjacent over hypotenuse. So this is adjacent and this is hypotenuse, and I'm really trying to find x here because sine is opposite over hypotenuse. So I need to find that value. So this is 11 squared plus x squared equals 13 squared, or 121 plus x squared equals 169. Subtract 121 on both sides, and I'm going to be left with x squared equals 48. Now this one's ugly because I can simplify the square root of 48. 4, 9, 16 comes out, right? So this is x going to be 4 root 3. So x is going to be 4 root 3 here. Now I'm looking for the sine value of this theta measurement. So when we have this parentheses, doing this right triangle and completing it satisfies the requirement for the inverse here, right? So this is done. Now I just need to find sine of theta. Now sine is opposite over a hypotenuse, so I'm going to have 4 root 3 over 13, final answer. So number 13 is going to be 4 root 3 over 13. I hope I didn't say 13 twice. Okay. Number 14. Ooh. Marker's going bad. No! Okay. Number 14, where am I? What happened? Okay, tan of inverse sine 5 over 6. Again, kind of the same problem as the last one. I know that 5 and 6 aren't on the unit circle, so I'm going to have to draw a right triangle and figure out my values. So again, sine is going to be positive, because I'm not looking for a negative value here, in quadrant 1. And we know that sine is opposite over hypotenuse. So I'm going to be doing Pythagorean theorem to find my adjacent value, because tan is adjacent anyway. So let's go with 5 squared plus x squared equals 6 squared. 25 plus x squared equals 36. Subtract 25 on both sides. And I'm going to x squared equals 11. Right? So I'm going to square both sides. So x is going to be the square root of 11. And I know now that I need tangent, because again, I've satisfied the inverse sine 5 over 6 part by drawing my right triangle. So tangent is opposite over adjacent. So it's going to be 5 over the square root of 11. But because I have the square root of 11 in the denominator, I need to rationalize the denominator. So I'll get 5 root 11 over 11, and that's my final answer. So number 14 is going to be 5 root 11 over 11. Last one in this set, number 15, is inverse cosine of cotangent pi over 2. We did one similar to this a little earlier. Now this one's not drawing a right triangle because clearly pi over 2 is on the unit circle, and it's the reverse, right? So when the inverse is on the outside, I know I'm going to have to evaluate as an exact for cotangent of pi over 2, and then I'll do the inverse of that in a minute. Now cotangent at pi over 2, well, pi over 2 is 0, 1. meaning x over y is going to be 0 over 1 or 0. So we've done this one a couple of times today alone, where we have a 0 value at cosine or sine, and cosine of 0 is going to be at 0. So my answer for number 15, answer is pi over 2. Okay, and that's the last one in this set. Okay, let's move forward and do some ABCDs of trig graphs. Okay. Number 16. Now again, we're going to do some trigonometry graphs. We're going to do one of each type, right? So we'll do one of each of the 6 types of functions. We'll find the ABCDs. We'll make a quick graph. And if there's any asymptotes with cosecant, secant, cotangent, and tangent, we'll also be able to identify those. We'll also do some domain and range when it comes to cosecant, secant, cotangent, and tangent. Domain and range with cosine and sine are a little bit easier, right? Because you know the domain will be all real numbers. It's just their range within that kind of road that we talk about. That will be the range part for those. So we can go ahead and bypass that for now. All right, number 16 will be our first and only sine function. So y is going to equal sine of theta plus 3 pi over 4 plus 1. Okay, so first we want to find the ABCDs, and then we'll go ahead and do a quick graph. So A is the amplitude, B is the period, C is the phase shift, and D is the midline. Okay, so the amplitude is A, and that's the number in front of the trig function. When there's nothing there, it's 1. It's not 0, it's 1. D is the last part of the function, so we're going to do this, and it's going to be up 1. We have to do direction for that, right? So the positive one means up 1. Now, the B value is always the coefficient of theta, or if there was something in between the trig function and the parentheses. There's nothing there. So remember what the default parent function's period is when it comes to sine and cosine for that matter, and that's 2 pi. So my period is going to be 2 pi for this particular function. Now, C is my phase shift. Remember, it's the opposite of what you believe it is. So instead of right 3 pi over 4, it's left. So this is going to be left 3 pi over 4. Okay. Now we've got all of our ABCDs, and we can go ahead and graph. So we want to graph the left 3 pi over 4 first. So this is a negative 3 pi over 4, and that's going to be my first value because we need 5 key points, right? So the next thing we want to do is we want to add the period to negative 3 pi over 4. Well, okay, we can do it off to the side because these aren't nice denominators, so we can go ahead and make them nice by combining like terms in terms of the denominators. So multiply by 4 on top and bottom. I'll have a negative 3 pi over 4 plus 8 pi over 4, which is 5 pi over 4, which is going to be my final or 5th value. So it's going to be 5 pi over 4 here, and that's my 5th point. Okay. Now we can go ahead and find the middle. We knew that the middle was 8 pi over 4 anyway. We had our first point of negative 3 pi over 4 and our 5th point of 5 pi over 4. Stay here, buddy. Titan, stay here, buddy. He's being a real crazy dude today. All right, we knew the middle or the distance was 8 pi over 4. So half of that is pi, right? Because that's 2 pi. So we know that there's a pi distance here where we can do just 4 pi over 4 subtracting, because that's half, right? So I could do minus 4 pi over 4, which will give me just pi over 4, right? Or 1 pi over 4, right? So what did I do? I took the entire period's distance of 8 pi over 4, divided it by 2, because if that's 2 pi, I can just do 1 pi, and then I would just subtract it from the distance here. So negative 3 pi over 4 plus 4 pi over 4 is 1 pi over 4, and then the distance there. And that's our third point. We would have our second and fourth points. If this is 1 pi to 5 pi, that's just 4 pi over 4. So this is 3 pi over 4. And this is going to be negative, ooh, this is actually negative. Sorry, negative pi over 4. Okay, so it's not exactly right there. It's more like there. Okay, now we can go ahead and make our other values here. So the midline is up 1. So we have a value of 1 here, which is dashed. Our amplitude is another 1, so we have a 2, which is going to be solid, and a 0, which is going to be solid. So the function is going to live within this roadmap here. We know that sine starts in the center, so let's go ahead and make sine start in the center here. Up to the top, back to the middle, to the bottom, to the middle. So here is our nice function for sine, and that is going to be sine equals, or sine of theta plus 3 pi over 4 plus 1. Okay? All my markers are dying. It's no good. Okay, let's go ahead to number 17, and we will do a cosine function. Number 17 is going to be y equals 3 cosine theta plus pi over 2 minus 1. Okay, so again, let's find our ABCDs. The a value in this case is going to be 3. The midline, or d, is going to be down 1. Our period, again, there's no value in front of theta, so that's just going to be 2 pi. And our phase shift is left pi over 2. Okay? Okay, let's go ahead and find our 5 key values. So left pi over 2 is going to be our first value, so negative pi over 2. The period is 2 pi, so I'm going to be adding 2 pi to negative pi over 2. So again, we can do that the long way. Negative pi over 2 plus 2 pi, make a common denominator. So this is negative pi over 2 plus 4 pi over 2, which is 3 pi over 2. So we'll make it here at 3 pi over 2. And again, if you're doing this without like graph paper or without radian measurements, you can eyeball it and it's probably going to be fine. You can make it as longer as you wanted to, because again, as long as your measurements are fine and there was no exact values there, you can eyeball it as best you can. All right. Okay, so that's our 5th value. Now, our 3rd value, again, if our period was 4 pi over 2, half of that is going to be 1 pi, or 2 pi over 2. So I'm just going to subtract 2 pi over 2 from this, which will give me pi over 2. Then our values in the middle, because I can't exactly have this, it's just going to be just pi. And then this one's just going to be, so this one's actually 0. And again, my measurements are a little bit off because I'm not exactly correct with the way I drew it. But again, you get the point and we're fine. So we have a negative pi over 2, a 0, a pi over 2, a 2 pi over 2, and a 3 pi over 2, which is like only half measurements, right, around the unit circle. Okay, so we've got our 5 points. Let's go ahead and graph it. We know that the midline is down 1, so I'll make a negative 1 here. Amplitude is 3, so 0, 1, 2. And then at negative 4. Okay, so again, cosine and sine live within the function. Cosine starts at the top. All right, so at negative pi over 2, we have a value at 2, to the middle at 0, to the bottom at pi over 2, to the middle at 2 pi over 2, and back to the top at 3 pi over 2. And we've got our nice function there. Okay. Okay, number 18 is going to be 3 cosecant 2 theta minus 1. Okay, so clearly we have a couple things that are different with cosecant and secant. One of the biggest things, obviously, is asymptotes, right? Now, these particular functions aren't going to have phase shifts, and you're not going to see phase shifts typically when we have a full cosecant or a full secant graph, because really we want to just focus on what the asymptotes are, where to plot them, and then where to put your points. So when it comes to anything with cosecant, secant, cotangent, and tangent, we still have to find our ABCDs, but some of these values may not be as important as our cosine and sine values. And moving forward, we'll run into those. So our a value for this cosecant function is 3. Our d value is going to be down 1. Our b value, now cosecant and secant also have a parent function period of 2 pi. So we have a value in front of theta here. So we're going to do 2 pi divided by 2, which is just pi. So the period for this particular function is just pi. And our c value here, there was no phase shift because there's no parentheses moving forward. Now, the key part of our asymptotes is how we remember asymptotes on cosecant and secant. So with cosecant, our asymptotes are at key points 1, 3, and 5. And we have actual values or points at 2 and 4. Now, why is that the case? Well, let's go ahead and draw a little unit circle over here to the side so we can try to realize or remember what the values are for cosecant that make asymptotes. Now remember, an asymptote is where the value or the answer after evaluation is undefined, meaning zeros in the denominator. So cosecant, remember, is 1 over sine, or 1 over y. Where are, the Titan here literally led right on my nose. Thanks, buddy. Where's the y value? 0 on the unit circle. Well, my y values are 0 at 0, pi, and 2 pi, 3 times. Now, on our base period of 2 pi here, 1 is 0, 3 is pi, and 5 is 2 pi. That's why we have asymptotes at those 3 points for cosecant, because we can't have 0 in the denominator at those 2 points. Now, at points of 2 and 4, it's reversed. Point 2 is actually pi over 2, meaning our second value on the unit circle. Well, at pi over 2, the point is 0, 1, where we have 1 over y is 1 over 1. So this is something to remember when we talk about cosecant, because this rule, asymptotes and points, are specific in this manner to cosecant. So let's go ahead and make our graph. This one should be relatively easy because there's no phase shift. Whenever there's no phase shift, it's usually very, very simple to graph. So there was no phase shift, so we have a point at 0, which is our first point. Our period is pi, which is our 5th point, which means our third value is pi over 2. And our, these should be dashes. And our other intermediate values are pi over 4, 2 pi over 4, and 3 pi over 4 here. Okay, so this is really just 180 degrees, or 1/2 revolution of our circle. Okay, down 1 was our midline. Amplitude was 3, so again, we're going to have a value here at 2, and we're going to have a value here at -4. Okay, now, before we get to the asymptotes, a really quick note about the road map. The road itself is perfect for sine and cosine because those two functions live within the road. But cosecant and secant are inverses of sine and cosine. So we draw the road still, but cosecant and secant live above and below that line, and they're shaped like quadratics kind of, so U's and N's, right? So we still draw the road because we need to know what is not going in the road, right? Because cosecant and secant are on the outsides. So let's go ahead and draw our asymptotes to identify where we can't make graphs. At points, key points 1, 3, and 5, we have asymptotes. So we're going to have an asymptote at key point 1, key point 3, and key point 5. Right? So we're going to have actual points at 2 and 4. Both cosecant and secant go top, bottom, top. So in our first value section here, we make a dot at the amplitude line, and we have our value. Here, again, we're going to go to the bottom. We're going to go to the bottom of the amplitude, or the minimum value, and that is our next value. This is our cosecant graph, 3 cosecant 2 theta minus 1. All right, number 19 is going to be our secant graph. So y equals 2 plus 3 secant theta over 2. Okay, so just like cosecant, the rules for secant are just about the same. The asymptotes and the points when we get to after our ABCDs are just a little bit different. So let's go ahead and do our ABCDs. The A value, don't get it twisted here, right? The A value is just 3 because the operator of the plus indicates that that 2 really should have been in the back because 2 is D. So this is going to be up 2 for our midline value. B, well, theta is really kind of next to, I know it looks on top, but it's next to 1/2. So secant's parent function period is 2 pi. So we're going to be doing 2 pi divided by 1/2, which ends up being 2 pi times 2, or 4 pi. So the period for this function is 4 pi, which is a really, really long period. And then C, there is no C value. There was no phase shift because there is no parentheses. Now, asymptotes for secant are exactly the opposite from cosecant. Asymptotes are at 2 and 4, where we have points at 1, 3, and 5. Okay, so let's go ahead and graph our function. Our first value is at 0. Our fifth value is at 4 pi, which is, again, a very long period. Middle value is going to be 2 pi because it's just half of the distance here. And then we're going to have our 2 and our 4 values of 1 pi and 3 pi. Really super simple frequency or interval right here, right? So up 2 is our D value. Amplitude is 3, so we're going to have a value at 5 and a value at -1. Okay. Asymptotes are at 2 and 4. Okay, which means we're going to have points at 1, 3, and 5. Again, secant, just like cosecant, top, bottom, top. So we're finding our top value at 1, I'm just going to make the half of that so you would know that it goes in the other half. And again, this is a really long period, a very wide period, so your actual secant graph is going to be pretty wide. 3 here at the bottom at 2 pi, and then back up here at the top for 5 pi, or 4 pi. Okay, and that's our graph for 2 plus 3 secant theta over 2. Tangent and cotangent, so we'll do the tangent one first. This is a simple one. It's y equals tangent of theta over 3. Okay, so tangent and cotangent operate differently than the other 4 functions, certainly. Tangent and cotangent both have asymptotes, but their periods normally are just pi, right? Because tangent goes from 0 over to pi, and when it comes back around, quadrant 3 is a little bit messy because tangent and cotangent are the only functions that are positive there. So we really kind of avoid that as best we can, because then things start to repeat after that value, right? So tangent of theta over 3. We're still going to find our ABCDs. You're going to find that the amplitude, however, is more like a vertical stretch. We don't plot the amplitude on tangent graphs, and because it would go through it, but the tangent function still, that squiggly still goes through the amplitude. So we don't usually graph the amplitude. It is important to know what the amplitude is, but again, it can be represented as a vertical stretch. So the amplitude is 1 here, but again, we don't need it because we don't plot that line. We don't draw that line. B is pi. Now this is 1 over 3. So what we have is pi divided by 1/3, which is pi times 3. So the period for this graph is going to be 3 pi. There is no phase shift, and the midline is 0. So asymptotes, that's also a little bit weird, okay, and points. Now when it comes to the key values of tangent and cotangent, we only need 1, 3, and 5. There is no 2 and 4. It's just 1, 3, and 5. Now, when it comes to tangent, there's only one asymptote, and that's at value 3, the middle value, right? We don't do 2 and 4, and the asymptote's just at 3 on tangent. So let's go ahead and graph it. We're still going to make 3 key points, again, not 5. So our first value is going to be at 0 because there was no phase shift. 3 pi is going to be my 5th value, and then the middle value is going to be 3 pi over 2, right? Half of the distance of its period. I don't have to draw anything else in terms of my 5 key points. Now, because the d value was 0, all of my dots or all of the squiggly turns are going to be at our key points here of 1 and 5. Asymptote at 3, which means all I have to do now is draw my function. Now again, a period of 3 pi is 3 times the size of its normal period. So we're going to go through 0. Now this should go a little bit closer to the asymptote, I apologize. And through 3 pi. So this is the graph of the function tangent of theta over 3. All right. Now its domain and range. Well, clearly its range is all real numbers because it's going to go from negative infinity to positive infinity. Its domain is going to change a little bit because we're looking for the values that are excluded as opposed to the values that are included, right? Because those have a pattern. Normally speaking, tangent values domain are in increments of pi over 2 plus pi k, meaning all values that start with pi over 2, then we add pi times k, where k is an integer. So 1, 2, 3, 4, 5, 6, 7, blah, 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 -1, -2, -3, whatever, right? 0 is also included in that because pi over 2 is the first interval that we have an asymptote. Now, whatever we do to the period, we must also do to the domain. So what did we do to the base period? Well, the base period or the parent period was pi. We multiplied that by 3. We have to multiply this whole domain by 3 as well. So our new domain is going to be all excluded values, so x cannot be 3 pi over 2 plus 3 pi k. So really what we're doing is we are distributing that 3, the 3 that we made the pi into, to both of those terms. Now let's take a look at what's happening here. We know that all excluded values are 3 pi over 2 plus 3 pi k, because take a look at our first excluded value. 3 pi over 2 is an asymptote, because if k was 0, all of that would cancel, and I'd be left with 3 pi over 2. So whatever we do to the period's base, meaning multiplication or division, we must also do the same thing to its domain. So here's our graph of tangent of theta over 3, asymptotes at 3 pi over 2 plus 3 pi k, and we have points at 0 and 3 pi. Okay, let's do a cotangent. Okay, number 21. Y equals, and it's kind of similar, but it'll be helpful because it is similar. I didn't make it that way, it just was luck. So we have a cotangent function, 3 cotangent theta over 3. Again, we're going to find the ABCDs, and just like tangent, the A value or amplitude is not super important. But when it comes to cotangent, again, our key points are going to be at 1, 3, and 5 only. There is no 2 and 4. But our asymptotes are now going to flip. They're going to be at 1 and 5, with the only key point going to be at 3. And again, the reason for that is because cotangent at point 3, where we have pi over 2 normally, would be 0, 1. And we know that cotangent is x over y, so 0 over 1 is an actual value of 0, where 1 and 5, I would be having 1 over 0 and negative 1 over 0, which is both undefined. So that's why we have asymptotes at 1 and 5 and actual points at 3, okay? So let's go ahead and do this. Our A value is 3. And again, all that's going to do is stretch the verticalness of this, and verticalness is now a word. Just put it in the dictionary for you. B, again, the base period is pi. So again, we're going to be multiplying it by 3 because that's the division of 1/3. Our phase shift is 0 and our midline is 0. Let's go ahead and graph our function. 0 is our first value. 3 pi again is going to be our fifth value, where we have our third value at 3 pi over 2. Now again, asymptotes are at 1 and 5. So cotangent's a lot easier to graph. Now cotangent starts high and goes low, as opposed to tangent starting low and going high. Start high and go through the middle point there. It's not bad because our D value or midline was here. So this is going to be our cotangent function. Now again, when we talk about values of its domain that it cannot be, the domain is really where x cannot be 0 plus pi k. So take a look at what's happening here, for example. When we have no phase shift, that means that the original value or the first value that we have is 0, or the first plottable value is 0. Clearly there's an asymptote at 0. That means that we're going to have every interval of pi that is going to be here. Now that's the parent rule or the base rule. But again, just like in tangent, what did we do to the period? We multiplied it by 3, which means I'm essentially multiplying this whole thing by 3 as well. So the domain for this particular function, right, is going to be where values of x cannot equal 3 times 0 is just 0 plus 3 pi k. Now that makes sense because take a look at these two specifically on this graph. We have an asymptote at 0 and we have an asymptote at 3 pi because k was 1, meaning the first interval past 0, which was 1. So 0 and 3 pi are asymptotes. And again, our next asymptote would be at 6 pi and 9 pi and 12 pi. And if I were to go backwards, it would be at negative 3 pi, right? So all integer values or integer multipliers to 3 pi. And 0 clearly was there too. Okay? Let's do one more thing. So when we talk about applications of sinusoidals, we really are talking about things that vary with time, but they vary in a similar pattern or in a cyclical pattern. So Ferris wheels are the biggest thing that we talk about, right? We can also talk about temperature over time and things to that nature. So it doesn't really matter what the basis of the problem is because it will always be the similar aspect of varying over time where it has the same pattern, right? So let's go ahead and say that we're on a Ferris wheel. Now, let's say that that Ferris wheel takes 5 seconds to reach a maximum height of 40 feet. So at 5 seconds, we reach a maximum height of 40 feet. Now, let's say that it takes 15 seconds for 1 revolution. Now, we only need one more piece of information, and let's go ahead and say that the diameter of that Ferris wheel, 18 feet. Now, the question is really this. Can you not only make a graph, but can you also make an equation or derive an equation from this information? And more importantly, are you able to plug in values for time, which would be t or x, and height or distance, which would be y, or whatever value of f of x or f of y, f of t even you would use? And the answer to all those things is yes, of course we can. So for this particular problem, in terms of time here, let's go ahead and make a graph and derive an equation from this information. So I know at 5 seconds I've got a Ferris wheel that gets to a 40-foot maximum height. So, put that in that straight. Let's say at 5 seconds, because we have the x-axis, which is time, in seconds. And we have the y-axis, which is going to be height, or feet, distance from the ground. So we have at 5 seconds, we have a 40-foot height. That is going to be our maximum value, or our amplitude. We know it takes 15 seconds to make a full revolution. So that means at the 20-second mark, 15 seconds later, we're going to have another max value at 40. Okay, so now we have something that would be represented as a period. The wheel is 18 feet in diameter. Okay, well that's important because that helps us find our minimum value. So if we get a 40-foot height here, I know that wheel is 18 feet in diameter, so my minimum value is going to be 22. Now, that's not super low to the ground. So you might be thinking to yourself, well, how did we get to a minimum value of 22? Well, if you think about any kind of amusement park ride, you typically have to go up on some kind of platform to get there. We can just say specifically that this platform is a little bit taller than normal, right? So 22 is going to be our min value, but where is the minimum value? Well, if we know that the period is 15 seconds long, and this is sinusoidal, or it has trigonometric sinusoidal properties, we know that it's going to vary over time, which means that the middle portion of this, or my third key point, if you will, is going to be the middle of these two values here. Well, 15, if that's the distance of the period, then 7.5 is going to be where I'm looking at. So this is going to be 12.5, and decimals are fine. That's going to be where my minimum lies. Now, this is actually the cosine value of this function. But we're not actually done yet, because when we talk about making an equation, I need the ABCDs, right? And to get that, I'm going to have to find just one more piece of information. Actually, two. And the one thing we need is the midline value, because these represent the height and lowest point, lowest point and highest point of our amplitude. That means the midline is going to have to go through somewhere right here. So if the distance here is 18, that means 9 is going to be the value that goes in between. So this is 31. Okay? And the last thing that we need is the period, but we'll do that when we get there. So the amplitude is 9, because that's the distance absolute value from the midline up to the top and the midline down to the bottom value. Our B value is the period. Well, we knew the period was 15, but that's just in terms of numbers, like our regular coordinate plane. We have to convert this over to radian measure. So we know that a sine and cosine value is going to be 2 pi over b. Well, our actual period, because we can't simplify that, is going to be 2 pi over 15. Now, C value, what was the phase shift? Well, we started 5 seconds in, so we're going to have a value here at right 5. And then our D value is going to be 31, so up 31. And there we have our ABCDs, so we can finally make our equation. So the equation, we know it's cosine because it starts at the top, is going to be 9 cosine 2 pi over 15. Leave it on the outside of the parentheses. You do not want to distribute that. And we can use x or theta. If it's right 5, it's a minus 5, and then plus 31. And we have our equation that represents the data that was given to us from my brain, because I made this up. Thanks for watching this episode of Titan Class. See you next time.